All right. Hi, everyone, and welcome to today's MIT Robotics Seminar. It's a pleasure for me to introduce today's speaker, Professor Sonia Chernova. Sonia is an associate professor in the College of Computing at Georgia Tech, where she's also the director of the Robot Autonomy and Interactive Learning Lab. Before becoming a faculty, she got her PhD from CMU, and she was actually a postdoc, here at the Media Lab. So Sonia's research focuses on robot learning, human-robot interaction, interpretable machine learning, with the goal of developing intelligent robots that can operate in a smart way in human-populated environments. Her work has been recognized with multiple awards, including the NSF Career Award, the ONR Young Investigator Award, the NASA Early Career Faculty Award, as well as multiple Best Paper Awards, including at top conferences such as HRI and ICRA. Since 2021, Sonia was the founding director of the NSF AI Caring Institute, which is a multi-university team developing AI systems to support elderly people experiencing cognitive decline. And she was also the general chair of CORAL, the Conference on Robot Learning, last year. So without further ado, let's welcome Sonia. Thank you so much for joining.
Thank you so much. Thank you so much for the introduction, and thank you all for being here and for the invitation to attend. I'm really excited to come give this talk. So we're going to talk today about algorithmic design of proactive and interpretable home robots, and hopefully I'll motivate the need for both of those in just a second. But for me, just speaking personally, I've been involved in robotics for a couple of decades. There are many, many worthwhile robotics problems. There's ocean exploration, there's environmental impact, there's space exploration, there's search and rescue, there's warehouses and logistics. And I enjoy working in all of them, but in particular, the home is the place I keep coming back to. And it presents sort of the ultimate challenge for robotics in many ways because of the complexity. How do we develop robots, whatever form factor they have, for assisting people with mundane things that we consider so easy and so trivial, yet remain so hard for robots. And so the overall goal of a lot of my work has been on how do we develop robust autonomous systems that operate in human environments. Now, we've done a lot of work towards this question. Over the past few years, it's spanned, how do robots locate objects in the environment? How do they recover from task failures? How do they grasp the objects they find in the right way in order to use them appropriately? Can we monitor the activity of humans within the homes in order to inform various aspects of the AI systems we develop? How do we safely navigate in our indoor as well as outdoor environments? Object rearrangement, which is how do you place objects from groceries to laundry to anything else within the home? And then there's these last two topics of proactive assistance and user interaction. And these are the two that I want to focus on today. But I wanted to mention these other areas largely because this is, I'm going to focus on, very narrowly on proactivity and the topics that it touches. But of course, there's so much more. There's so much more needed to, to have robots actually be functional and useful in a home setting. But let's talk about proactivity for a second. Let's say we have a home robot. That robot, when we want it to perform various tasks, falls on a spectrum in terms of its capabilities. It can be responsively assistant or proactively assistant. And this is the difference between me having to say, please put the dishes in the sink, and me saying, thanks for cleaning my kitchen. And a lot of our research, I would say majority of our research, especially in the day of LLMs, where suddenly everyone can talk to a robot, falls on the left side of that spectrum. A lot of papers right now, there's a lot going on there. And that's very, very worthwhile research. We want to be able to talk to robots. It's actually very important. But I think there's a lot of really critical challenges, the ones I want to focus on the right side of the spectrum. And let me focus really briefly on why. So first of all, I want to take this quick example of this work on low-level speech. This is a great paper called Fox-Poser out of Stanford last year. And it allows us to use machine learning to enable robots to follow tasks like close the drawer, take out my toast, and so on. What I want you to look at is the examples, and imagine yourself using this type of system. For example, let's see, take out the bread from the toaster and lay it flat on the board. Right? Can you do this? Yes. Should you do this occasionally? Yes. But if you do this day to day, it requires an incredible amount of human effort, and particularly your attention. Right? At that point, you're really having to work very closely with the robot. Over time, that's going to be very, very tiring. The other significant factor that kind of makes the case for proactivity is the practicality of the timing. Robots are slow. That video I just showed you was 8x. Okay? Let's watch a video from, in this case, Google. Many of us have seen this video, right? This is the Palm Saycan video in which the robot is asked for help. I'm going to use it as an example. Of course, the contribution is really, again, on how do you ground language and allow robots to reason about how to help. But I want you to pay attention to the timing with which the robot provides assistance when it has been asked for help. Okay. Robots, for the foreseeable future, are going to be a bit slow, where they're very safe, but there is an element of having to wait. And this is a practical consideration, right? I mean, we need them to be slow to be safe and so on, but if we want efficiency, if we want this thing to be truly useful, what do you imagine a robot being? You imagine it anticipating what you need, right? And making sure that it fulfills that need on time without creating this element of waiting. So aside from my own opinion, there's also, just want to highlight this great work by a variety of authors from the HRI community that's a few years old now, where they actually conducted user studies of verbally tasked or reactive or proactive robots, and also there found that users generally would like proactivity, right? When we imagine Rosie the robot, when we imagine our future robot butlers, we imagine them doing things without being asked. With the caveat that if something goes wrong, I want to be able to talk to the robot. So again, we want the left side of the spectrum where we want to be able to task robots through language. We just don't want to do it all the time, okay? So hopefully I've sold you on the need for proactivity. I want to show you one last video from existing work. This is from Coral 2023, Mascaro et al. And it shows another example of proactivity. And I want to show this one because it's a typical example of how the robotics community has been approaching proactivity. In a lot of our applications, a lot of work on tabletop coordination. I've done some of it. Others, many more people have as well. Things like in a manufacturing setting, the robot anticipates I need a screwdriver, it hands you a screwdriver. In this video, the robot anticipated that the user wanted a drink, correctly predicted when they were ready for that drink and poured the drink. Again, really, really effective use of proactivity. But one thing I want to point out is the level of perception needed in order to carry out this level of proactivity. You need to be monitoring several objects, real-time movement of the person, their intent, and have a really carefully placed camera in order to do so. And this will work for a variety of settings. This will work for controlled manufacturing settings in many cases, or potentially even a standard kitchen if instrumented correctly. But the domain I want to address is the home, where the idea that you're going to have carefully placed cameras from a variety, capturing the scene from a variety of angles, anticipating user needs, and being able to do that in the long term is a little bit impractical, right? There's no way to instrument a house in this way without violating privacy, and even if you're willing to violate privacy, maintaining those cameras, making sure they're not knocked off, and so on is really challenging. So this is the problem we set out to sort of explore when we started this project, which is how can we provide, have a robot provide proactive assistance across the entire home? And just to put a little bit of a constraint on it, when I say assistance, that could mean many things. In our case, it's largely pick and place tasks, like fetching you water, getting your cereal out of the cupboard, putting your dishes into the sink, stuff like that. I don't mean assistance like I proactively built the IKEA furniture that you brought home last week. That's more complicated. So in particular, we're focusing on pick and place assistance for repetitive, predictable, and hopefully low stakes tasks. Okay? Great. So within that context, I'm going to, for the rest of the time, talk about 4 different projects in 2 different categories. The first is going to talk about the proactivity. How do we do that? And we've explored 3 different ways. We started out very, very strictly about making a kind of a worst case assumption about what information we might have. I'll motivate that in just a second. And then we expanded and loosened that assumption and added more data. We addressed other things that we saw pop up along the way, which is like personalization. And then I'll also talk about another piece that's really important in this context. It's important in general, too, in robotics, but interpretability of robotic systems or the connection to explainable AI or explainability in general is important. But when you have a robot that's being proactive, right, you didn't ask it to do something and it's now doing something in your kitchen, the ability to ask why are you doing that? What are you doing? Becomes really important. And so now we have this connection back to explainability that I want to talk about as well. Feel free to ask me questions throughout. I like conversations, and I'm happy to take questions at any time. So first, I'll talk about this first piece, which is on can we do proactivity with just time and objects, and what do I mean by that? So we want 3 things. We want the proactivity, I already motivated. We want longitudinal assistance, and by that, I'm trying to differentiate from the real-time assistance of I'm doing something, oh, looks like you need a screwdriver, let me fetch you a screwdriver in real time, okay? What we're trying to do is predict further out into the future so that the robot has time to perform the actions needed, fetch your bowls, fetch your cereal, put away the dishes, without you having to stand there waiting, right, for that action to complete. So we're looking at longer time horizons, minutes, potentially hours, instead of seconds. And the last thing is larger workspaces in the sense that we're not looking at a tabletop, but more of an entire room or even multiple rooms. We're looking at an entire house. Okay? And so our first approach, because of the definition of assistance I gave you earlier, which is that we're largely focusing on pick and place of objects, if you think about the fact that you're trying to assist by moving objects around from place to place, and then you say, well, what is the minimal amount of information I need in order to achieve my goal? The minimal amount of information is, can you track objects and how they move over time? Who moved them? Why they moved them? What task they were doing when they moved them? What if we don't know any of those things? Right? So the first step, it's a little extreme, but let's see what we can get with just assuming that we can see objects teleport throughout the space. We can track that, and we can provide assistance. And then we'll relax that assumption, okay? Now, we needed data to do this, and there's not really any longitudinal data collected about how people use objects in a very, very long setting that we could find. If you know of any, please let me know. But we collected a data set and released it using MIT's virtual home simulator. And thank you for releasing that, folks. And there we crowdsourced, first we went online, crowdsourced lots of daily schedules, daily habits and all kinds of stuff. Then we hired a team of undergrads to write scripts. So if someone said that they ate breakfast, we had a whole team of different people code multiple different breakfasts, and we could probabilistically sample across that. So we ended up with a lot of diversity of human behaviors that we grouped into different personas or personalities or households. So this is examples of 2 households. Left and right, each horizontal line represents activities throughout a day. This is 40 different days. You can see somebody on the left really doesn't leave their home at all, is just always doing something. Person on the right leaves for various periods of time. But you have a lot of variability across these. This is one of the more, this is probably one of the least variable. But you get behaviors like this person eats breakfast every day. That was actually relatively rare. Some of our participants don't eat breakfast. Some eat breakfast 50% of the time. But when they do dishes is very variable. That's this teal line, is very variable in timing. Some jobs are not done every day, like laundry and so on. And last but not least, the types of objects they use. And this is too detailed to look at on a slide, but the types of objects that are used each day also are not necessarily consistent. This is the data we're working with when I report results and when we train our models. We've tested this on real-world settings that are much smaller, but with simulation, we're able to test on dozens of simulated human schedules based on what our participants have told us that they do throughout the day. So how do we model this data? So when we have a robot in an environment, in a home setting, how do we go from its understanding of the world and the objects that it sees to being able to provide proactive assistance? And we formulate this problem largely as a graph neural network, and in particular, generative graph neural network. So we have a bunch of objects. We represent them as a scene graph to represent how objects are placed within the home, where they're placed, in what room, on what surface, and so on. Okay? In order to predict how the robot can assist the user, it takes the current scene graph and predicts what the scene graph will look like at some arbitrary time in the future. You can pick 5 minutes, 15 minutes, 2 hours, and so on. So we want to have a generative model predict the changes in this graph over time. Okay? Let's imagine we have a breakfast activity that uses these objects, so milk, bowl, spoon, and cereal. In order to predict changes, what we need to do is predict that they went from their original locations in the cabinet and the refrigerator over to the table for someone to use. And we can do that. In order to do that, we kind of condition on the current locations of the objects and the current time. And then we utilize edge-to-edge message passing in order to predict the likely changes which occur. Now, there's a little bit of a caveat here, because edge-to-edge message passing requires the topology. It uses the direct topology of the graph that you have. And we have this, while semantically all these objects make sense together in the context of a breakfast, we have this milk that's topologically located in the fridge instead of on the counter. So a really critical piece of the model here, of the underlying model, is that we have a soft topology, kind of pseudo-edges that have been created within this graph that connect semantically similar objects. And you can use an embedding for this, right, and figure out how closely related various objects are from a semantic level. But milk and cereal, or the ability to put that in a bowl and a spoon, I didn't draw all the edges here. They're semantically similar, right? And that enables the message passing, the edge-to-edge message passing, to enable to actual correct generalization to future time steps. Our last piece of context here is, of course, the time, because time of day really influences the behavior of objects in the house. And so we can do that. We can take this current graph, take the current time, encode all of this into a model, and be able to predict the future graph at some point in time.
Do you predict just the topology of the graph, or there is also geometric information for each object?
So the question is there geometric information of each object? And right now, there's not. There's geometric information about the map of the environment that the robot has in order to perform navigation, for example. So if we go to the kitchen, it has a geometric map to do that. But this model does not use that information. And if I show you the results, kind of an abstract variant of the results, I want to highlight that there are, when we perform this kind of assistance or this kind of prediction, there are various outcomes, positive and negative, that we want or don't want. And I want to look at them separately. So first of all, the environment itself is full of objects we never really interact with, like a potted plant, right? A potted plant largely sits in one place and should hopefully stay there. And hopefully that is an unused object that was correctly untouched by the robot. If you start moving my potted plant around for no reason, that starts to get inconvenient. So hopefully we want a very high number of correctly untouched objects. We want a very small number of incorrectly moved objects. Out of the objects that the person actually touched or used, we would like them to be that the robot correctly predicted where they're going to move, and as little as possible to have incorrect destinations. It would be very, very bad to say, I know what, you're going to be playing tennis later. I'm going to take your tennis bag and hide it under the bed, right? Like that's really the worst case here. And then missed is like, yeah, I wasn't sure if you were going to eat breakfast or not, so I didn't make anything, right? That's missed is like I would prefer, that's the conservative answer, is I couldn't predict anything, so I didn't touch it. I didn't put it anywhere strange. And so our current results for this very, very early model look like this, that over 99% of things that you shouldn't touch are not touched. This is great. And then of the things that are used, we largely are very conservative. This has to do with the model and the kind of behaviors that we have in our distribution. A lot of 50-50 breakfasts. If it's 50-50, it just doesn't predict anything. But then very, very low incorrect destination. So when it does decide that it needs to provide assistance, so in almost 40% of cases, it is correct. So 40% of the time, it anticipated what you wanted. And we consider that really, really good for this particular data set. Now, of course, in the model that I presented so far, you know, there's two fundamental limitations, but they both have to do with the structure and the assumptions that we've made. One is that we're only really using object locations. They don't tell us everything about the world, about the person, what they've done. And then, as a result, we have a Markov assumption here. So there's a little bit of a limited scope here. And I think we can do better, right? And so that brings us to our second variant of this work, which is to say, OK, now that we know what we can get from objects, what if we extend this to also include other things we know about the human? And there are many places you can get information about humans these days, right? If we wear Fitbits, Apple Watches, whatever your preference, right, you can theoretically get activity data from that. Or you can have a smart home with activity recognition, like we have in some of our other projects that my lab is doing. And so you could maybe have cameras and so on. So I don't care where that information comes from. For us, it's actually going to come from activity recognition, but very, very abstract. But the question is, how can we modify this model in order to make use of other pieces of information? So instead of conditioning on single, just global context, which is time, in this case, we're going to condition on a latent vector containing more information. And in particular, we're going to use a recurrent model over a time series of past latent vectors in order to allow us to condition on the entire history of latent states that have been occurring over time. Finally, in order to add more information, we're going to be learning an autoencoder to encode information from either any kind of input that we have, such as activity labels. But an important aspect of this is we don't want to over-rely on them, right? So that because, again, the reason we didn't go with activity recognition from the beginning is I don't truly believe I can get 100% accurate 100% of the time activity recognition within the home. The one way you could maybe do it, and even then I'm skeptical, is by having your robot follow the person around room to room nonstop. And believe me, people would get very sick of it very, very quickly. And I don't think it would help, right? I mean, from a proactivity standpoint. OK? And so now we have all of these different types of information together and this new model. And we actually changed two things here, right? This was our original model. I'm going to call it STOT. I didn't give it a name earlier. They changed two things. One was we added history. And there's a little bit of an abstraction. There's a little bit more than that. But one of the things we changed was history. And the other thing is we actually added the information coming from activity labels. So there's two changes for the model. Just to be clear about where the contributions are coming from, we're going to run an ablation study and understand the benefits of both of these algorithmic changes. But very briefly, and again, there's like details in various papers, but what we see is that if we add history, we see a huge jump, right? And that makes a lot of sense. That was one of the things we shortcut in the original work, was we were really conditioning on just the current situation and time. And that, understandably, is limited. If I know that this is what the world looks like, but I don't have any memory about whether you already ate breakfast or not, obviously you're going to get something wrong. So we get a boost just from that. And we get another about 10% boost from using activity labels. But in this case, really interestingly, I was expecting a much higher boost. And there's a limit to how much you're going to get here, because the inherent behavior we're trying to predict is just, in some ways, unpredictable, right? It's probabilistically derived and has this natural variance. But the other cool benefit of this model, this expanded model, is that you can predict further and further into the future. So the blue is our older work, and its accuracy declined further out into about an hour into the future, versus our new model is actually very, very stable, and that's really cool. Now, the cool thing that we did, or that I find exciting as a roboticist, is that this can run on an actual robot. So this is hard to see because it's trying to show different variants. We put this together for a paper. We have a stretch here on the left, watching the person having breakfast. We are very happy to be users of Hydra from MIT as part of this system for modeling objects. This is a slightly edited version of Hydra where we made the objects move dynamically, and there's some changes there, but it's underneath is Hydra itself. And so in order to start this entire process, the robot does have to watch you go about your routine a few times. On our simulated data, you don't need more than 5 days of data, roughly 5 iterations through your routine. In order to get reasonable performance, it really depends on the complexity of the task, of course, and the quality of your observations.
As a clarification, for the graph neural network, you predict with the fixed delta t, for example, what is the seeing graph 1 minute from now, and then if you want to predict over a longer horizon, you predict.
You do it again. Yep. You just keep repeating. All right. And one of the other things that I'm going to skip showing here is that, of course, now that we have this entire architecture, one of the things you could do is say, I'm not actually sure if the person is going to eat breakfast today or not. The natural thing to do would be to ask, right? And so we do have an extension of this within this project where the robot does ask. I'm going to skip it for the sake of time, but you can ask clarifying questions and say, okay, are you going to eat breakfast today or not? Or do you want cereal or oatmeal today? It affects the proactivity a little bit because there's a question of timing, but there's other assumptions here as well. Last but not least, I want to just briefly show what we've been up to more recently. And as Luca mentioned, I'm part of a team working with on an AI institute focused on older adults and older elder care. And there's some, both in the context of that as well as other factors, some really interesting questions came up, like, should the robot do everything that you do? Right? And the natural answer is, of course, likely not. But if you've been thinking about it, you might have thought of some things like, so let's say I come in and I'm going to just throw my jacket on the floor, or throw my dirty laundry on the floor. Okay, your robot's watching, right? So tomorrow it's going to carefully drive over there and throw your laundry on the floor. That's not what you want. But aside from copying our own bad habits, there are certain personal preferences we might have, or maybe we want to reinforce better habits as well. And in the context of older adults, the way this has come up is that there's this thing our medical collaborators always say is, use it or lose it, right? If you're working with folks who already are experiencing cognitive decline relating to age, if you don't use your skill, you're not going to have that skill for much longer. And some of the older adults we work with are very adamant that, don't make this robot do too much. I want to be able to keep doing these things. I want to continue cooking. I don't want robots that cook. I find it not only fun but stimulating, and if I stop doing it, I'm going to lose some of that mental capacity. And so in other words, this is not a one-off solution. I can't just write a rule. This is incredibly personalized. By the way, to start this project, we went and interviewed several older adults and had the lowest agreement score we've ever had among a survey. They all told us about over 100 tasks that they want robots to do, not want robots to do. And you you calculate the agreement score between their responses, and it's 0.2. Right? It's the lowest agreement score ever. Everyone wants completely different things. And so you really need a lot of personalization. So we've been playing with that right now. We have a stretch. It can do many things. It can fetch your umbrella. It can fetch your keys. It can fetch your medication. It can make you cereal. It can grind your coffee, all kinds of things. And again, when we survey people, they all want different things. Some people say, yeah, please, I want you to put the groceries away. Others said, absolutely not. I want to know where everything is. And if you put something somewhere, I won't be able to find it. And so what we came up with is an interesting way to try to build on all of that feedback and to personalize the robot system by regulating what proactive behaviors it exhibits. But to make this as personalized as possible and to make the personalization generalizable. So for example, here on the right, it's making a smoothie, which is a rather loud activity. The user potentially says, stop, I'm trying to sleep. You're making too much noise. You have a few options. You can learn a rule that says, don't use the blender at 3:03 p.m. because maybe that happens to be the time. That's a very narrow rule and is not in the spirit of the feedback you were given, right? The feedback you were given is don't do loud things like blending while I'm sleeping. It's not about the time. So you have to very carefully reason about the scope and the generalization of that feedback. And that's what we've been trying to do. And interestingly, we've had a great success with large language models. And one of the great uses for large language models has been in analyzing the semantic similarities between various activities. We will benchmark against ChatGPT, or do benchmark against ChatGPT. And it can do some of that reasoning itself. It could tell you not to blend something while someone's sleeping, actually. And here are the results. But it isn't personalizable. Remember, coming back to that idea that there's so little agreement. As soon as we have a little bit of feedback, our algorithm is just able to get what people want at a higher success rate than ChatGPT. Again, it's averaging across too many people and not getting that personalized element, even if you feed back all the feedback that somebody gave it, right? We're not withholding anything. You feed back all the feedback that the users give it, and it's still not personalizing quite enough. That may change with future large language models. As always, it's a moving target. But this is one interesting thing we've been exploring. OK. Yeah? So the question is, should we be engineering our environments? Should we meet robots halfway, right? Should we engineer our environments to help facilitate the operation of robots, which would in turn not only improve their overall autonomy, but improve the timing and make proactivity a little bit less critical? I agree with you, and I think that will happen. Actually, earlier today, we were talking about potentially putting QR codes on your plates and objects or cabinets. Like, I don't care. Like, I would, especially if there's ways to make them pretty, right? I could annotate my kitchen more if I could have a robot butler. Like, maybe I would be willing to do that, right? I think there are things that as these technologies mature, people will meet them part way. But I don't think that takes away the need for proactivity entirely, right? There's still a burden to constantly have to tell someone. For those of us with significant others and spouses, right, think about the difference between doing something proactively and a pleasant surprise for someone versus being like, hey, can you buy me flowers? right? Like, there's a big difference there, and I know that I'm taking it a little too far as an example because there's an emotional element there, but it's still like that, right? Like, you want to just have it done without you having to nag, right? There's a difference. Great. All right, so let me talk at the very end there of that video. If you were paying attention to the video instead of me, which is great, you might have seen that one of the things we can do with this type of generalization is actually explain why the robot chose to do something or not do something. And I want to talk about that topic a little bit more now. Because again, when we have robots be proactive, I think people will ask why. So the question is, what if you move to a new house, right?
Yeah, or maybe another way to say it is like the person's routine changes.
Changes. So continual learning, yeah. Right? And does continual. So right now we don't have this framed as a continual learning problem, which is a big shortcoming, and I think there's like a low-hanging fruit to try to make this continual learning. Because the robot's continuing to move around and observe, you could, at the worst case, retrain the model, which is kind of dumb. But you could frame it better as a continual learning problem. That would account for gradual things, gradual changes. Where it will fail is significant changes. Like the whole family went on vacation. There's a video I'm thinking about from a robot movie competition that was really, really sad about people leaving a robot behind, and it continues to serve them coffee day after day, but there's nobody present in the house. It's actually incredibly depressing video, but anyway, there's all kinds of abrupt changes, like when we go on vacation or the holidays start, and suddenly you're home and no longer going to work and sleeping in, and I think we haven't tested, like bulletproof tested the model with life changes like that. Yeah? Okay. All right, so I want to talk about explainable AI for a bit, and this is gonna be a bit of a change, right, in topic. And in particular, I want to talk about this work that my student Devlina Das and our collaborator Bean Kim, who's an MIT alum, have been doing, and it's focused on concept-based exploration for autonomous agents, particularly agents that perform sequential decision-making. If you follow the field of explainable AI, right, explainable AI or interpretable machine learning are all about how do you provide insights into the decision-making of a black box system. When that black box system is making many, many decisions over a period of time, that becomes incredibly challenging. But one of the things that we've seen in the field over the last few years is there's been this push towards formalizing what explanations should be, what a good explanation. It's not just about dumping out the attention weights. It's not about saying, well, this feature is weighted more heavily than this other feature, but abstracting up into actual concepts that mean something in the context of a task. And so this first started out in computer vision, where explainable AI has been used for a while, where people originally started with some sort of regions or grad cam for those who have seen it, right? So pixel spaces, this is the heat map of why I think this is a bird or whatever it is. And then followed on by this work by Ko et al. In 2020 that said, hold on, if I abstract from pixels to actual concepts like the wing color of a bird, the undertail color of a bird, like those are the things that humans would use to describe a bird, right? The beak, the legs, the tail, undertail. Two things happen. We can explain things better, and actually the model learns better. You get this dual benefit to both sides of the coin. Now, in their work, those concepts had to be defined by an expert. So the experts in medical imaging sat down and wrote down, bone spurs, blah, blah, blah. They trained those concepts, and then they went But we were looking at agents and sequential decision-making agents and saying, well, can we do something similar? Not images, but now decision-making in time. And so, you know, a lot of our research questions were, you know, coming back to this idea of concepts. What are the useful concepts or abstractions for decision-making systems, for robotic systems? How do we represent them, extract them? How do we learn from them? And can we get that dual benefit? Can we make agents learn faster and explain themselves better? And in particularly, this is known as the protege effect in some of the literature, right? Where psychological phenomenon that teaching or explaining material to others can benefit the learner themselves. Right, and this is the way we're trying to do it. We have, so, yes? Yeah. The short answer is, can we do this? Can we do this is, of course, yes. The way we do this is we take this idea of concept-based explanations, we merge it with this idea of joint embeddings that we've seen across the literature for all kinds of things, state and action models, state and command, image and text, and we merge this thing and leverage state explanation joint embeddings in order to achieve this dual benefit. There's one caveat to what I'm about to describe. We published this in NeurIPS. It's fully on simulated agents and in particular games. I know this is a robotics talk, but there's still a step to take with robotic systems. So for this particular approach, we've done other explainability work in robotic systems, but I'm particularly excited about the promise of this one because it has what's called high fidelity for the explanations. And you'll see that as I describe it, that the explanations are true to the actual decision-making of the deep RL model. It's not an approximation or a guess as to why I think the model. It's true to the actual model and its reasoning. And this is a very, very important objective in explainable AI, right? Having high fidelity of explanations that are not approximations. And so we're going to use two games. Sorry about that, but first I want to define what a concept-based explanation is. And in the context of this work, we're going to define a concept-based explanation as a natural language phrase that enumerates a set of concepts, each of which describe a particular state-action pair and in the context of some goal. So for example, let's play the game Connect 4. I think most of us are very familiar with it. An example would be, let's play column 4 because it provides center dominance and creates a 3 in a row. Okay? So these are two different concepts, both of which apply to the state and action of playing, the state of the board and the action of playing that move. The actual framework that we contribute is called state to explanation, S2E. And it consists of 3 parts that I'll describe really briefly. So first, we train a joint embedding that maps states to explanations of why those states are good or bad. You lose the game, the other agent went and you lost the game. That's okay, that's trivial, that's a loss of a game, but there's other explanations, and I'll show you them in a second, that we're able to capture as well. Once we have a model that's a joint embedding between explanations and states, we use it to train an RL agent using reward shaping. I'll talk about that in a second. And then, once the model is trained and now frozen, we can run it, we can execute it, and we can understand or interpret the reasons for its actions using those same explanations generated from that same embedding. Okay, so going through those 3 in a little bit more detail, for the joint embedding model, we take as input the explanation. We assume here that we have access for the very first, just for this first part, to some expert who tells us about the domain. Okay? They tell you things like 4 in a row wins the game, right? Or if your opponent has 3 in a row and you block them, that's good. So these are not very complex concepts, and you can often get them out of rule books, which is what we did. Okay? You should have access to this. We have the current state, the previous state, the current state in order to encode what changed. And then we have a little bit of an extra label that tells you just a binary variable that tells you, for example, if the game is over. Like, did you win, did you lose, or whatever. And then whether this is a positive or negative data sample, because what we're going to do is use a contrastive loss function that's going to minimize the L2 norm distance when the concepts are aligned, maximize that distance when they're not aligned in order to learn the joint embedding the way you normally do. So our two domains are going to be Lunar Lander and Connect 4. This text is probably a little bit small for some of you to see in the back, but the concepts that we get out of these various rule books are things like creates 4 in a row, blocks the opponent win, or on the Lunar Lander, decrease tilt, encourage left leg contact with the ground, conserve fuel usage, conserve or land without crashing, and so on. We had a simulator, played lots of games. We were able to get lots of data, generous amount of data that we split into train, validation, and test. And then we evaluated all 3 phases of our system. And so very, very briefly, first of all, can we learn a joint embedding? Yes, yes we can. It works really, really well for Lunar Lander. It works actually less well for Connect 4, which surprised us at first, but turns out that a lot of concepts are a lot of states of the board simultaneously are attributed to so many concepts or multiple concepts, right? You could be advancing yourself and giving yourself a 3 in a row while blocking the other player's win. And so picking the one most important concept is hard, but if you top 3, then yeah, you're doing really well. It's just an issue of how you label the data. So in the end, it does learn the joint embedding really well. And then when we run RL, we run it in the traditional way, but now we have reward shaping directly coming from this joint embedding space right here, which evaluates the state of the board. Just very briefly, when on the Connect 4, we can run RL without any expert data, and we beat that by a lot. But also, when we do have expert-based, so other people have generated expert-based, so reward shaping from an expert for Connect 4. When we take their code, we perform roughly on par, like very, very similar to their performance, which is great. Right? Because we didn't have an expert coaching the system throughout. The only place we used an expert was to encode what are good strategies in Connect 4, right? But we're performing on par with an expert-driven mu0. And then for Lunar Lander, there is no reward shaping variant. And in this slide, it's just way too slow to even compare to. But again, we perform on par with expert-defined reward shaping. And so everything's looking great. That means we got our first win. The first win was, do we improve actual learning? The answer is yes. And then on the explainability side, we can now generate explanations using this embedding. And this is what I meant by high fidelity for this work. If I back up for a second, because when we ran RL, it was using the same embedding to generate rewards, so that when it uses that embedding again, then to generate explanations, right? It's the same embedding generating both, and so we get that benefit of fidelity. One thing I'll just very briefly mention, if you can see, the frame rate for Lunar Lander is kind of high, right? And if you do this, an additional challenge for us is that I can generate explanations for every state, but you can't read them because there's too many of them. They're going by too fast. And so what's the practical use of any explainable AI if it's spamming you with feedback? So we actually, there's extra work that we did on grouping and filtering and simplifying these explanations in a temporal context. I won't go into it now, but it was an important part of the user experience for sure to be able to do that. And then we recruited participants on Mechanical Turk. And we had them do this. We had them interact with our explanations. Because to me, there's a whole other conversation I can have with you guys about what does it mean to have a good explanation. I'm short of time, so I should wrap up, but say that if it has an effect on people's performance, then they got the information and it was useful. It wasn't just, oh yeah, that sounds good. No, I want it to be useful. And what you see is that in terms of our explanations, in this case it's the gray line, and in this case it's this teal line. This is before they had their explanations versus after. You see this huge improvement in performance, which is what you want to see. The other line to maybe consider looking at here is the none. If they had no explanation and they just had time to practice, they're not doing as well. They're getting bored and not really improving because they're not seeing the point, I guess. I'm not sure. So that's just a quick takeaway. So in summary, concept-based explanations. This particular approach I'm very, very excited about because of this two-way benefit to both agents. But to wrap up, bringing it all together, again, coming back to this idea of reactivity versus proactivity, to me, not only is proactivity important, but the relationship of proactivity to explainable behavior, to transparency, being able to build robots that are intuitive about, that we are intuitive to users about why they performed some task. And with that, I just want to wrap up by thanking all the wonderful co-authors that have contributed to the work that I talked about, and to NSF and Amazon for sponsoring the work, and to you all for listening, and thank you, and I'll take any questions.
Fantastic talk. So we should have time for a few questions.
Okay, so you mentioned how this last project that we looked at was only applied in games. And so I was wondering, what are some of the challenges they anticipate in applying this in real-world robotic systems?
That's a great question. So this particular, because of its focus on reinforcement learning, I mean, mainly the places where we had an expensive data was in training the joint embedding, and then in actually training the RL policy. There is a sim to real transfer element here we could explore, and I'd love to explore at some point. But that's why we didn't. We were really just fascinated by the concept of could we do this, and wanted to do this in a way that didn't jeopardize the project. Data is always the challenge, right? That's the typical answer here. But I think it's really, really interesting potentially as coupled with sim to real. Yeah.
Going to the home robotics application, so you gathered a bunch of data about people's personal tasks, and you also briefly mentioned the possibility of like a family going on vacation. So did you think in detail about like a family home where multiple people are living there and they each have their own preferences, and how to deal with all those things that might not align?
That's a great question. Right now, especially in the early work, it doesn't matter who has what preferences, because it's just tracking objects. And so one of the powers of that simpler method was that it didn't matter how many people were there or what they were doing. The robot really didn't know. But now that we're actually using activity recognition, that's where it becomes important to understand who is doing the activity, and you need to actually identify it. So we haven't tested it, is the other answer, but so far the early work I know is robust to that. We should try it out. And we're expanding that system this year and testing it in so we've tested it on a real robot in a single room. We're going to multi-room. It's introducing all kinds of challenges about actually tracking and the movement of those objects and getting accurate timings for that. So that's what we're exploring in the coming year.
Thanks.
For the Connect 4 example, the agent suggests to move the red piece to the middle because it creates a 3 in a row. But actually doing so would ensure that the player wins the game in one move, for the specific example. How difficult would it be for the agent to provide explanations that talk about what happens in the future in 1 or 2 or 3 time steps?
As long as the model actually can think about it and simulate it forward and be accurate, I think you could. We've explored something similar with chess. What's the open source? I'm blanking out on the name of the open source engine for chess. But we did it with more of alpha-beta pruning and so on, and talking about giving explanations. I'm so proud of that study for many reasons, but one was we had Turkers come back and participate 3 days in a row in a longitudinal context, 3 days, but for Turkers, that's pretty amazing. They showed marked improvement in their chess performance thanks to the explanations that were generated. So I still think that that's super cool. But, and those were closer to what you're talking about, that they talked about sort of a little bit the hypotheticals, that the potential of a not just the concrete state, but the potential of a state. That requires the model to also actually plan ahead, right? So I think it's very much doable, but it's not something that we do.
Thank you.
Yeah.
I was wondering, have you done any interviews when people expect the robots to be reactive and when people want the robot to be proactive?
So that paper that I showed earlier that Minoru Asada, Maya Chakmak are on, and Battaglia, I think, is the first author, IJRR 2017. They explored it in a study, and that's the main paper I'm aware of that explores that question. Now, they did it with university students, as far as I remember, so I think it's really population dependent and would be interesting to explore that study with other populations. But I recommend checking out their paper.
Thanks for picking me. Sonia, I think maybe if the last question especially is, like, what are the, in your perspective, the interesting research questions going forward? And particularly interested in, because you're exploring these proactive actions, I think most of the examples you gave were around how using the information that a robot already collected, how can it proactively provide service to the user? But what about robot proactively understanding what is lacking and exploring, gathering more resources or asking questions?
Those are fantastic open problems, right? And Andrea Bobu, who just walked out, has done a little bit of work on that area in the context of robot learning. I think we need to do more of that context in the context of proactivity, right? The biggest limitation of our robotic systems in most cases, there's many, but that they don't know what they don't know, right? And the more we can develop systems that first identify that they don't know something and then go out and try to actually obtain that information, the better. It ties back into, in the simplest form, for the robot to understand where objects might be, which objects it should be tracking. That's an incredibly simple form of that. What you're talking about is much more involved and I think is absolutely worth pursuing in the future. But these are huge research projects on their own. The more we can encode uncertainty, but not just true uncertainty, uncertainty at the fundamental level of knowledge, I think the more intelligent our systems can be.
Right, Sonia, thank you so much.
Thank you.